that is verification of a sampling theorem. So in this case, okay, so here we, in case of sampling the signal, we have a analog signal. I'm just opening the pointer here. Okay, we have the analog signal which is continuously varying, so continuous time varying signal. Our objective is to convert it into samples, that is discrete time signal. So that's the objective of sampling theorem. And how do we do that? That is the overall story of sampling theorem. So the input here in this case is a continuous time signal, and we want to convert it into a discrete time signal, such as, or something like this. X of t is the normal notation used to represent a continuous time varying signal. We want to convert it into x of n. That means we do not want to have the amplitude variations of a signal at every instant of time, but we want to observe the amplitude variations only at a specific time instant. That is, we are moving from x of t to x of n. Why do we do this? Because when we want to represent an analog signal as a digital signal, the first step what we do is cut that signal into different pieces, that is called as samples, in the time axis. And of course, then we also manage the amplitude and represent every piece of the signal as a bit pattern, 0, 0, 0, 1, and so on. That becomes totally a digital representation of the analog signal. But the first step, what we do here, is sampling the signal. That is what we study in today's presentation. So what's the purpose? It is easy to code. Code means representing in a coded format, or easy to store and also to transmit. So basically, we want to deal with the digital signal. In that case, if our input is currently analog, for example, a voice signal or a video signal, we want to maybe store it somewhere in a digital format, or even to transmit it. Because when we convert the analog signal into digital, we have more flexibility. We can do many operations on that very easily than being in analog itself. So to do all that, we convert analog into digital. The first step here, what we do is we have to sample the signal. So that's the idea of sampling. So here, if you see this figure, this is a continuous time signal, right? Here, everything varying with respect to time. So here we have the time axis, and we have the amplitude variations along the y-axis here. So at any instant of time, you have a value here for the amplitude, right? Maybe it's a voltage or power and something. For example, here is a 0, and the next instant you have 0.0001, 0.002, and so on, up to 1, and so on. We can have many pieces here. I mean, we can divide this time into infinite number of divisions and observe what is the amplitude at that point here. That is a story of continuous time signal. But we want to convert this continuous time signal into discrete time signal. That's what we do in sampling. So in case of discrete time signal, how it should appear like? We are concentrating on only some of the time instants. For example, here, exactly where my pointer is, it is written as 1 here. What is the amplitude here? It is some value, right? Maybe 1 volt. And then 2 here. What's the amplitude here? Some value, maybe 5 volts. Maybe next to 3. Time is 3, then what is the amplitude here? It is something else, right? Maybe 2.5 and so on. So instead, that continues here along the time axis. So instead of observing what is the amplitude or value of the signal for every minute time instant, we are restricting our observation to only to some of the instants of time, selected instants of time. What's the value here, right? So at 1, at 2, 3, 4, and so on. What's the value? Instead of at 0.0001, 0.0002, and so on, we can have any level of precision there. So that becomes a continuous time signal. Instead of that, we are making it into discrete. Only at some instant of time, we collect or we notice what's the value of the amplitude or value of the signal. So that's the discrete time signal. So how do we do that? That is sampling. So here, it is an intermediate step in digitization of the analog signal. So if we want to convert analog into digital, that is a continuously time-varying signal into digital in the form of bits 0, 1, 0, 0, 1, 0, 0, 1, 0, and so on. That is digital. So in that step, this sampling is the intermediate step. So in this case, we are cutting the time axis into different pieces. One sample here, second sample here, third sample here, and so on. And then observing what's the value at that particular time instant, right? So that is the intermediate step here. That's why I have written here, it's intermediate step in converting analog into digital. And now we will see in more detail how the sampling looks like. For example, this is the analog signal. It has continuous variations when you consider any time instant. And now we want to convert this continuous time signal into discrete time. So in order to do that, we use something called as a signal, and the signal that looks something like this. We use different pulses here. They look like pulses, right? This is called as comb function. These are the different pulses. They are uniformly spaced. So we basically multiply this, and then generate a discrete signal like this. So what is the meaning here? This is a sample signal. What's the meaning here? So instead of collecting the amplitude value of this signal at every instant of time, we will collect the amplitude value at this point, at this point, at this point, and so on. So those points where do we need to collect is defined by this. The spacing here defines where you need to collect the amplitude values. For example, if there are only 3 pulses here, one is here, suppose another one is here, and third one is here, then you will be collecting the value here, and you will be collecting the value here, and you will be collecting the value here. 3 different instants only you're collecting. Since there are 3, 6, and 9 pulses here, you can collect 9 amplitudes from this. That is what's shown here. On the other side also, the same process continues. So this is the idea of sampling. So here, after sampling, the signal should be recoverable. That means you want to transmit the signal, analog signal as a digital signal. Okay, first you do the sampling. But when you want to reproduce the signal, that should be reproducible. So we need to do the sampling in this way. That means by considering the final objective as recovering the signal. So now the question is, how frequent these pulses should be? Or in other words, if there is an analog signal, we want to chop it or we want to break it at different time instants. So how many pieces shall we make so that it is recoverable at the receiver? Because based on the number of pieces you make, your recoverability will be influenced. For example, if this is the variation here, I collect one sample here, this value is 1 volt, and next I collect another value here, that is maybe 0.7 volts. So then if I try to represent this signal, and I have one value here as 0.5, other value as 0.7 only, I do not have these amplitude values. Instead, if I had collected here, as well as here, as well as here and here, then I would have a better estimate of this signal value, overall value here, when I try to recover that. So I have this note here. So how frequently you collect the samples from this signal, that will decide the recoverability, whether you can clearly represent the signal again in the same way as of the original signal or not. So to do that, how frequently we need to collect the value? That is given by something called a sampling theorem. So you might have heard about Shannon and Nyquist. We have discussed, I think, in other courses. So they gave this idea of the sampling rate, how frequently we need to collect the samples or values from the continuous varying time signal. So here is the statement of the sampling theorem. The sampling theorem states that a band limited signal with the certain bandwidth W. I will tell you what is band limited signal. Okay, you have a signal that has some bandwidth W, then it can be regenerated with all original information if the rate of sampling f is at least twice the bandwidth of the original waveform. The condition is here. So how frequently you need to cut the continuous time signal to make it into discrete or while sampling? So that is given by this key relationship. So the sampling frequency, how frequently you need to sample, that depends on what's the maximum frequency of the signal you want to sample. For example, you have a signal of bandwidth W, that is the maximum frequency of this particular waveform. Then your sampling frequency must be equal to 2 times or must be more than 2 times of the frequency of your signal. That's the idea of sampling theorem. So I told you here it's a band limited signal. Band limited signal looks something like this. So it means it has some bandwidth as defined between these lines here, and inside this bandwidth, a range of frequencies, it has some value. And after that, its value is 0. So that's the band limited signal. So you can consider maybe your signal has a bandwidth of 100 kilohertz or 3 kilohertz, any value. So based on that, you need to decide how frequently you need to cut it so that you can represent it very clearly. It is reproducible because that is the objective. In the previous slide, you have seen what's the objective of sampling. You need to reproduce that, regenerate that. So you must follow this relationship to sample so that this signal can be regenerated or represented as similar to the input signal. For example, you have the continuous time signal here, and these are the different instants of sampling. That means here we are going to collect what is the amplitude value, and then at this point here we are going to collect what's the amplitude value, and then at this time we are going to collect what's the amplitude value, and so on. Similarly here we are collecting the amplitude value here, and at this point what's the amplitude value here. So these pulses will guide us where to collect the amplitude values. So once you collect the amplitude values, it looks something like this here, where you have collected. Only at those time instants you have some value, and here we are not collected anything, so there is no value. We are not representing that. Okay, one practical example is a voice signal. For example, in case of a telephone, the voice signal, what we generate, maybe it vary up to 3 kilohertz, around 3 kilohertz. Then when it has to be transmitted, the telephone circuit will do the sampling. What's the sampling rate? This is the practical sampling rate, that is 8 kilohertz. So since 8 kilohertz is greater than 3 kilohertz, this relationship is obeyed here. So in order to sample 3 kilohertz signal, we need at least 6 kilohertz or more than that. That is what this says. The sampling frequency is more than that, or at least equal to 2 times the bandwidth of the signal. So we use the 8 kilohertz signal to sample in case of telephony. Okay, this idea of sampling or sampling theorem is proposed by Nyquist and Shannon. It's called as Nyquist-Shannon's sampling theorem. And we have another keyword here, Nyquist rate. That is nothing but this relationship. The sampling rate is 2 times or more than that. That is the Nyquist rate. That is called as Nyquist rate. Okay, when we do this sampling, there are different cases we can consider. The first one is whether the sampling is done at a frequency less than 2 times the highest frequency or 2 times the bandwidth. Yes, if it is done, then it is called as undersampling. Next case, sampling, is it done at a frequency equal to 2 times the highest component? Then it is called as Nyquist rate sampling. The third case, where sampling is done at a frequency greater than 2 times the bandwidth, then it is called as oversampling. So we have seen in the previous slide the sampling theorem. It has given us the freedom to choose the sampling frequency either here or here, right? Yes. So if you use this, that is, if the sampling frequency is less than the double the highest frequency component of the signal or bandwidth of the signal, then what happens? The signal reconstruction is impaired. That means you cannot reproduce the signal completely with the exact format or form of the original input signal. But in these 2 cases, the signal reconstruction is normal. That means if you try to reproduce the original signal, you can get almost the original signal. But in this case, it is not possible. This is what the discovery of Nyquist sampling theorem. So the proof we can find in the literatures why this should be equal to 2 or greater than 2. But there is a simple intuition. If you consider a sine wave, you consider just one wave. So you have a positive half and negative half. So if you collect 2 samples, maybe one in the positive half, another in the negative half, then you can represent a sine wave, right? One at the top, I mean, one on the positive side, one on the negative side. So that is equal to, that satisfies this condition. You have one sine wave, just one frequency, one positive half, negative half. That is one cycle. So you collect 2 samples from it. Yes, you can almost represent a sine wave, right? Or if you collect more samples from it, of course, you can easily represent. But if you collect just one sample in a sine wave, where the either you may collect from the positive half or negative half, then you cannot represent as a sine wave, right? So that's the issue with undersampling. So this is a simple intuition to think about the Nyquist sampling rate. He said, or they said, this should be 2 times or more than 2 times. Of course, a formal proof you can find in the literatures. Okay, so if the sampling is done at a frequency less than 2 times the maximum frequency of the signal, then that is called as undersampling, and that leads to something called as aliasing. So this will prevent the reconstruction of the signal in its original format. So we will see what is that. For example, you have the input signal here, and this figure here, there are many dots. That represents that this was sampled at a quite higher frequency. I mean, maybe 2 times or more than 2 times this was sampled. So you have many dots here. They are the sampling instants. Okay, this is signal here, this bottom part. This is the alias signal. So here, this is the original signal, but this was sampled only at here, 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 as well as here. Then if you try to reproduce a signal, what do we represent? We just represent this, right? The lowest frequency here. So now this low frequency signal is representing all those higher frequency components. So it's not representing what the original frequency components were. Okay? So there is a mismatch in the time as well as amplitude. We are not exactly representing where was the original frequency's amplitude or time was. Okay? This is called as aliasing. So these low frequency are occupying this place instead of occupying the original positions or somewhere very near to the original position. This process will inhibit us from reproducing the original signal. So this is the aliasing effect. Okay, again, a quick look at all these cases. For example, here it says the sampling is done at 2.6 times the maximum frequency. Here it is 2 times the maximum frequency. These are okay, right? Because the sampling frequency is greater than or equal to 2 times. That's okay. But these 2 cases, sampling is done at 1.4 times the maximum frequency. Here 0.8 times the maximum frequency. These leads to undersampling or aliasing. For example, blue color here, that indicates the original signal. The red color here indicates where you're going to sample it. So if you do more sampling, of course, you can represent more data from it or more values from it. And you can reproduce it in a better way because you have more values. You know more values here, so you can easily reproduce it. But in this case, if you consider one cycle, one value is collected here. And again, one value is collected here. So the green color here, that represents the reproduced signal. So reproduction is not same as the blue signal because it do not know where it has to represent the amplitudes because it did not collect during sampling at a rate of 1.4 times. Here, similarly, 0.8 times. It will represent one sample here, another sample here, another sample here. When you reproduce the green color, the reproduced signal, the representation is not anywhere near.
Okay, let us see the other part, that is regeneration of the signal. Until now, we have seen how to sample the given continuous analog signal. Now we will see how to reconstruct the signal. So we use the interpolation method to reconstruct the original signal from the samples. So this figure here, the first figure, shows the sampled signal, and the second figure shows the reconstructed signal using interpolation method here. So we use the command used in MATLAB to reconstruct the signal is given here, the MATLAB command. So basically, the first figure here is the sinusoidal variation of the sampled signal, and the second one is the reconstructed signal. We will see how it is done. So in the MATLAB code, it's a 3-line code shown here, but the keyword here is the command used to reconstruct the signal from the samples. So that's the third line here. We use the interpolation to reconstruct the signal. So interpolation is done with the help of this command, interp. So the first line here, t is equal to 0 to 1, varying with the instance of 1 by 10 power minus 3. So this is the time variation, and x is equal to sine of 2 pi, some frequency 30, and time. So x will have the sinusoidal variations, that's amplitude variations, for different time values as defined by t. And then, so that is the input signal, that's this signal, the first waveform. And then we draw the output signal, that's a reconstructed signal y, that is equal to interpolation of x comma 4. So x is the sampled signal, x comma 4 what is done here. You can see the second figure here. So it means the number 4 indicates if in the original signal X has some number of samples, then in the reconstructed signal Y will have the number of samples 4 times more than the signal that was in the X or the sampled signal. For instance, if this signal, the first signal, has, you assume like there are 20 samples here, that is X, the first signal. The second signal Y should have 80 samples, right? That is 4 times the number of samples in X. So you can see here we have more population in the second graph compared to the first graph. First graph has some samples, but they are very far away compared to the second one. In the second case, the samples are very close to each other, right? So that's the way of performing the interpolation. So by performing the interpolation, we get an estimate of the original signal that we actually sampled. So this is how the interpolation is done to regenerate the signal. So we mainly use the command interp. In this case, interp x, 4. The number here indicates what is the multiplying factor. So that number of times the number of samples will be increased. For example, in the sampled signal X has 10 samples, then the reconstructed signal will have 40 samples, and so on. You can have any number here. As you have more numbers, higher number, you will have more number of samples. Okay, this is the method of regeneration of the signal, that's interpolation, that we will use in our code. Okay, now I will go to explain the code. The MATLAB code is already given to you. So the different steps what we have learned in general so far, we will see how to implement that with the help of MATLAB commands. So first line here, first, second and third line, they are the basic commands here: CLC, clear screen, and clear all, close all. So that is mainly used to clear the contents or close all the open tabs. And then from here onwards, actually the the program starts to perform the sampling theorem and reconstruction. The first line here, we have defined a variable t final. It has a value of 0.05. And we will be using this value later in the later part of the code. We'll see that. So in the next line here, time varies from 0 to t final. So basically we want to define define different values for time. So we have defined here t final. So the time will vary from 0 to 0.05, which is defined by t final, with the increment of 0.0001. So time along the x-axis or time axis, we have variation starting from 0, 0.00001, 0.0002, and so on until t final. And then we need to consider an input signal, analog signal that we want to sample. So that value is held by this variable fd. So fd is equal to input. What we need to input? We need to input some frequency. So this we need to do while we run the code, because we need to have an analog signal for sampling, right? So what's the sampling, input signal's frequency? So that is defined here. That you can enter maybe 1000 hertz or 500 hertz, some value. And accordingly, we will be generating an analog signal. So analog signal is defined here. Xt is equal to cos of 2 pi, the frequency that you entered, and then the time. So time value is defined here, right? So xt will have the cosine amplitude variations for different values of time, right? As the time value varies, at every time instant you will have some amplitude value that is varying in a cosine manner, right? That is held by xt. So xt is basically a cosine wave having this frequency and the amplitude values are defined at different time instants. Those time instants are defined here with the increment of 0.00001. It's a very small variation. So when you draw this cos signal, it looks like a continuously varying analog signal. Okay, so this is the first signal that we have generated. So basically we need an analog signal to sample. So that signal we have generated. Now we will try to plot that analog signal. So we call a figure. Figure is a command used when you want to draw something, plot something. And then we have the subplot command here. Subplot command 4,1,1. It indicates that we want to draw 4 subfigures in this main figure. One page, we want to draw 4 subfigures as one column. And this is the first subfigure there, or subplot there. And we are going to plot what? We are going to plot x and xt. That means we want to draw t and xt. We want to draw the cos signal. So in the cos signal is drawn for different time values, and those cosine variation of the amplitude xt is plotted. So this is the horizontal axis, this is the vertical axis. That's the meaning. And this cosine wave is plotted in green color. G indicates the color of the plot. It's in green color. And then we will title it as analog signal, and we will name the axis. So time axis or x label is nothing but time. The y label, along the y direction you have amplitude, that is x of t. So this is how we draw the analog signal. And then what we need to do? We need to investigate different sampling cases that we have already studied, right? I told you we have 3 cases to investigate. The first one is undersampling. So in case of undersampling, what's the condition? The sampling frequency is less than 2 times the maximum input frequency what you have assigned. So we will consider that for the undersampling case, the sampling frequency is fs1, that is less than 2 times ft. So less than means it can be 1.3 or 1.4, any value less than 2. So we will consider here as it as 1.3 times the input frequency. So that becomes a sampling frequency. So this represents an undersampling case because the sampling frequency is less than 2 times the input frequency, maximum frequency component. And then okay, so right now we have chosen this as the sampling frequency. Now we will define here another term, n1. N1 varies from 0 to t final, that we have already noticed what is t final value, with the increment of 1 by fs1. Okay, so fs1 we have defined, so 1 by fs1. So basically this is the time instance. So this represents the time axis. Okay, so in this time axis we have variations from 0 to t final with the variations of, or with the increments of 1 by fs1. Okay, and then this one xn1 represents a y-axis. What is that? That's a cosine variation of 2 pi f and n1. So what is n1 here? N1 is this. It varies from 0 to 1 by fs1 plus 1 by fs1 plus 1 by fs1 until t final, right? So that is represented by n1 here. So again here, n1 in general represents a time axis. Time varies in this way. When the time varies, we are noticing or capturing the amplitudes, which is the cosine variation, at different values of time as defined here. And then we are going to plot it as a second plot, that's a subplot in the same figure. So the second subplot is mentioned here, number 2. Since these are the, n1 and xn1 are discrete values, we use a stem command. Stem command is to plot the discrete values. For example, for every value of n1, what is the xn1 value? So that is drawn with the help of, or plotted with the help of stem command. Okay, because these are discrete values, sampled values. So I have given some explanation here. Stem of x comma y plots the data sequence y for the specified values of x. Here we are going to represent the amplitude xn1, which is having a cosine variation for different time instants of n1 here. Okay, then we title it as an undersampling case. Okay, so this is regarding the undersampling. So at this moment, what we have plotted is nothing but the undersampled version of the original signal, right? So initially I mentioned when I talked about the theory of sampling, we will use an analog signal and also like a comb signal, and we multiply them and we generate the sample version. But actually we do that here in a different way, that is here. So this is the key point. Since 1 by fs1 is a larger value, because fs1 is a lower frequency, right? So what happens here? 1 by fs1 is a larger value. That means we are considering the samples xn1 at these instants. I mean at larger time gaps when you compare with the previous case, that's analog signal, right? In case of analog signal, what we did was we consider time t. T is having a variation of very minute variation. But in this case, our time here, n1, what's the variation here? The variation is according to this. It is not very minute. It is bigger than the previous case, right? So that means we will be capturing the amplitudes only at these instants. That looks like a sampled version. So it is not a continuous variation. We are not capturing every minute amplitude. We will be capturing the amplitudes only at these instants, 1 by fs1, 1 by fs1, and so on. Since fs1 is a lower value than before, I mean it's an undersampling case, so we do not have so many samples. Now we will consider another case, that is Nyquist sampling. So in case of Nyquist sampling, the condition is the sampling frequency is exactly equal to 2 times the frequency component, input frequency component. So here we define that fs2 is equal to 2 times the input frequency, and we will define the time axis n2 that varies from 0 to t final with a variation of 1 by fs2. So we have defined fs2 here. So now okay, fs2 is a larger value now, right? Compared to the undersampling case. In case of undersampling, what was the situation? fs1, right? That is 1.3 times fd. Okay, so this is a smaller frequency. So when you take the inverse 1 by fs1, the time becomes more, right? Time gap becomes more. In this case, we have a higher frequency than the undersampling case, right? fs2 is 2 times fd, so higher frequency. So 1 by inverse is a lower value, right? Lower than the previous undersampling case. So time instants are very small here, very close, right? As a result, when we draw when we consider xn2, which is nothing but we are capturing the amplitudes having a cosine variation, that is 2 pi fd and en2, right? So n2 comes from here at these intervals. So these intervals are much smaller compared to the undersampling case because the frequency is higher here. That means we will be having more samples in this case, in case of Nyquist sampling, while comparing to the undersampling case. and then we will plot it as a third sub figure in the main figure, and the values are represented as, or actually the values are plotted using stem command, because this is again a discrete variation of en2. N2 is having a variation at 1 by fs2. Every 1 by fs2 instance you have the variation for n2, and xn2 the corresponding amplitude variations. Okay, so and we will title it as Nyquist sampling. And then we will see the third case, that is oversampling. So in case of oversampling, we consider the sampling frequency fs3. This should be fs3. It is greater than 2 times the fd. So here fs3 is equal to 5 times fd. Any value greater than 2 works. So here we consider it as 5 times fd. And we will define the time variation here and corresponding amplitude variation here, because we want to plot this, right? So n3 is equal to, it will have a variation from 0 to t final with the increment in the time as 1 by fs3. So at every 1 by fs3 we will be collecting a sample, and we will be assigning that sample to xn3, right? So that is what cos of 2 pi fd multiplied by n3. So n3 comes from here with these gaps. So you notice here the 3 cases. The oversampling one has a very high frequency compared to the previous 2 cases. As a result, this time value is much smaller compared to the other 2 cases, right? Undersampling and Nyquist sampling. So since the time value is much smaller, you will be collecting xn3 very frequently than the earlier 2 cases, right? That's a case of oversampling. And okay, then we will plot it. This is the 4th sub figure in the figure, and yeah, stem is used to plot actually these n3 and xn3, and we will title it as oversampling. Now we have investigated 3 cases. We will see how it looks like. So I will go to display this value here. So far what we have discussed, the code, we will see how it looks like when we execute that. So first we need to enter the input frequency. We had the command to input the enter frequency, right? So input frequency, you can enter it as 500, 200, 1000, or any input value. And then then we had a figure. Figure had 4 subplots, right? 1, 2, 3, 4. The first one is the analog signal having a green color. That is what we have defined. So it has a frequency of 500. And then the second subplot was undersampling case, where the sampling frequency was 1.3 times of this, right? So we collected the samples, not very frequent samples. Once in a while we collected the samples, right? So if you consider 1 cycle here, then we did not collect so many samples. On an average, we collected 1.3 times the number of cycles here. And then Nyquist sampling, the third case. So in case of Nyquist sampling, the sampling frequency was maintained as 2 times the analog signal here. Okay, so that means if you have 1 cycle, then you will have 1 positive, 1 negative, again 1 positive, 1 negative, so on, 2 times in 1 cycle. And then let me show you. Okay, and then the 4th one is oversampling. Oversampling, we collected 5 times number of 5 times more than the input frequency. So you can see here 1, 2, 3, 4, 5. In 1 cycle we have 5 samples, and so on. Same continues throughout the duration of the analog signal. So this is how we have plotted the 3 different cases. First one is the undersampling here, The second one is Nyquist sampling. Third one is oversampling. Okay, right now we have done the sampling part. Now we need to reconstruct it because that's the objective of sampling. When we sample it, we should be in a position to reconstruct it. How can we do that? We will see the remaining part of the code that is given to you. So as I mentioned earlier, we will be using interpolation to reconstruct the signal. So that part is here, interpolation of the sampled signal. So right now the input for us is these sampled signals. I will show you. These sampled signals, for example, undersampling or Nyquist sampling or oversampling are the sampled signal. Using these, if we try to reconstruct the original signal, which is a cause signal, so how that appears? So that's what we are going to investigate in the remaining part of the code, that is interpolation. Okay, we'll begin the interpolation here. Initially, we will redraw the original analog signal just for our reference. So that is what done here. We will define a figure and a subplot, and we'll plot t and xt, which is nothing but the analog signal, which is having a cosine variation. Okay, then from here onwards, we will try to investigate if we reconstruct the undersampled version, then how that would appear like. Next, Nyquist sampled signal, how it would be. The third case, oversampled signal, how that appears. Okay, so we will first consider the undersampled version. So we will define a variable here xr1, that is nothing but interpolation of xn1 comma 2. So we have already seen the meaning of interp interpolation. What happens when you write interp xn1 comma 2? So this number 2 will represent how many times you want to increase the number of samples, right? For example, xn1, what is xn1? Xn1 is nothing but the undersampled signal, right? I will just go back to show you what is xn1. So here is xn1. From here, the xn1 value comes. xn1 is what? It is the undersampled version, right? Undersampled values or the samples. Now we are going to reconstruct that here in this part. Here, interpolation of xn1 comma 2. So we want to have double the number of samples what we actually had with xn1. Okay, and when we want to represent the amplitudes, we also need to have time, right? Time is also made double, 2 times. That means for every time variation, we have some amplitude variation, right? So both are 2 times, because if you have a time value, then you will have an amplitude value. So corresponding amplitude values we should match, right? So that's why both are increased by a value of 2 here. So n1, you know, n1 is the time instant of undersampled version as done earlier. So basically interpolation will increase the number of samples of the undersampled version by 2 times, both the amplitudes as well as the time. They are represented by xr1 and nr1 here. Okay, then we want to plot it. So we call the subplot here. The second figure here, or second subplot, will be the reconstruction of undersampled version. And we are going to plot it nr1 and xr1. So this is the time axis nr1, and this is the amplitude axis xr1. And we will name it as undersampled signal, which is reconstructed version. Similarly, we do for Nyquist sampled as well as oversampled versions. Now we are here in this part of the code, we are trying to reconstruct the Nyquist sampled signal. So xr2 here, the first line, xr2 is equal to interpolation of xn2. So from where xn2 comes from? Xn2 comes from the Nyquist sampled version. If you want, I can just go back and show you xn2. So here, in case of Nyquist sampling, we use the variable xn2. xn2 is nothing but cos of 2 pi frequency and en2 here. So these are actually the sampled signals, Nyquist rate sampled signal. We are trying to reconstruct using this interpolation command, and that is done at a rate of 2 times. So XR2 will have twice the number of samples that we used for Nyquist sampling, and corresponding time variations NR2 of En2 is represented here. And then we are going to use the subplot command as a third subfigure, and we will plot it. That is, for every NR2 time instant, we will be noticing what is XR2, the amplitude variation, and we will be plotting that, and we call it as Nyquist sampled signal. That's a reconstructed signal. And similarly we do for the third one, that is oversampled version. So XR3 is nothing but interpolation of XN3. XN3 is the sampled, oversampled signal, and that is increased by a value of 2. I mean, in terms of number of samples are increased. Here the time is increased by a factor of 2. So initially if we had 200 samples, now we will be having 400 samples, and we will be plotting that NR3 and XR3, and we will title it as oversampled signal. Okay, so now how this looks like. Basically, these were the sampled signals that we used to reconstruct. Suppose if we use this undersampled signal, then how it looks like when you reconstruct it. It should look something like this, right? So we have captured more number of samples here, right? Double the number of samples. And then Nyquist sampling here. So Nyquist sampling, you are reconstructing the Nyquist sampled signal. So is it almost similar to the input signal? So input signal already we have mentioned here. This is analog input signal. So when you want to reconstruct, all these reconstructed signals should be almost like this. But in the undersampled case, it is not near to the analog signal, right? The frequency has changed here. That's because we sampled this at a lower rate. When we try to reconstruct it, of course, we cannot represent this as similar to the analog input signal. So this process I mentioned as aliasing, because the frequency variations are higher here, so many cycles here, but here the cycles are very less, right? So instead of high frequencies, what you want to represent here, these low frequencies have occupied those places. So that's the effect that's called as aliasing. And then the second case, what we have observed is Nyquist sampled signal. This is the second case. So we have reconstructed it, but still it is almost similar to the analog signal, but not very similar to the analog signal. But this is almost enough based on the Nyquist theorem. It says we can almost reconstruct the signal if the sampling was done at a Nyquist rate. Nyquist rate is 2 times the sampling frequency or more than 2 times. So Nyquist sampling was done at 2 times. So it is almost similar to the analog signal. We have almost every information from the analog signal. Here, third one is oversampled signal. So this looks almost same as the analog signal, right? Because the sampling here was done at 5 times and we reconstructed it. So here it's almost similar in terms of frequency and amplitude as that of the analog signal. Okay, this is how we reconstruct the signal using interpolation. Now we can make some inference here. The alias frequency is computed as the difference between the input frequency and the sampling frequency. For example, if your input frequency is 200 hertz, your sampling is done at 1.3 times the input frequency, then you get a difference of 60 hertz. You have a negative sign that represents 180-degree phase shift. So in this example, I mean, when we plotted this, we considered this as 500 hertz, and we performed the undersampling at 1.3 times 500 hertz. So that difference between 500 and 1.3 times of 500, that becomes aliasing here in case of aliasing frequency in case of undersampled signal. So this is how to interpret the code. So I explained you the sampling cases, how it is done with the help of this MATLAB commands, and also explained you the second part, that is reconstruction using interpolation. We reconstructed the three cases, right? For three cases like undersampling, Nyquist sampling, and oversampling. So the same code we will try to execute in MATLAB. So now,
So here I have pasted the same code. Now I will run the code. While running, I need to enter the input data. So input data is nothing but the input frequency that of the analog signal we want to plot. So the input frequency I have considered here as 500, and then I press enter. So that right now the code is running, and I'm expecting two figures here. The first figure, in the first figure, I will observe the, as shown here, I will observe the analog. So here is the first figure. Here I have the analog signal, and then three cases. First one is the undersampled version, next is the Nyquist sampled version, and third one is oversampled version. This is what we have already seen. And the second figure, it's here. So in the second figure, we will be displaying the reconstructed versions. So that's basically interpolation. So here, the reference analog input signal, and this is the undersampled version. So you may observe here, it has a much lower frequency compared to the analog signal here. So instead of having many cycles as in the analog signal here, it has only few cycles here. So all your high frequency components are replaced here by a low frequency component. That's what the idea of aliasing here. And then we have the Nyquist sampled case. So in this plot, if you observe, it's almost similar to the analog input signal, but some information is not very clear, right? When you compare with the analog signal. But of course, you can represent almost every information that you have in the analog signal when you reconstruct using the Nyquist sampling case. The third case, what we have here is the oversampled signal. So this is basically the reconstruction. So this reconstruction is very similar to the analog input signal, right? And these are the two investigations we did in the code. We can have one more observation here, that is an additional observation. So let me define a command here, that's the sound command. So here, what I will be observing right now is how this analog signal is heard. So I use the command here, sound. And then we'll compare the reconstructed signals for the three cases, undersampling, Nyquist sampling, and oversampling, how those sounds are heard. And then we will have a comparison. So first case, I'm going to run here, sound of x comma xt. So I should define here some frequency. So the frequency, let me assign it as maybe 5000, and then I press enter and the code will run. This is the sound of original signal, and this is the display for frequency of 5000 hertz. And then I will use the same command for the first case, that's the reconstruction using undersampled version. So I should be reconstructing this, right? XR1. So how it is heard? So let me run the same code for the same frequency. So the frequency is 5000 and I'm going to run it, and please hear this sound. Yes, that is a very small beep, right? Now we have got some comparison of the original signal and the reconstructed signal for the first case. And now I'm going to run the same code for the second case. That is basically I'll be running XR2 variable for the same frequency. So I will assign the same frequency 5000 and how this frequency is heard. I mean, this reconstructed signal is heard. Yes, it's again a beep with the much sharp sound, right? And this is the display. And in the third case, I will be running the third part of the code. So let me run XR3 for the same frequency. So the frequency I'm going to assign is 5000, and you please hear the sound for XR3. Okay, I'm running the code. Okay, again now here you heard the sound and it's almost similar to the input sound, right? I mean input signal. So these are the three cases we investigated, and these are the additional observations. Maybe in your syllabus you don't need to do this, but these are just additional observations using sound command. Okay, so this is the end of this presentation. You try to run the code by yourself and present the outputs in the next session.